Hi there. This video is going to walk through a few key ideas relating to the first law of thermodynamics, which essentially tells us how energy goes into or out of our system. The first way that we can exchange energy with our system is by changing the temperature. So we can either add heat or remove heat from the system. And we always follow the direction of heat. So we would say heat is going into the system, or heat is leaving the system, or the system loses heat. So let's specify what we consider our system and what we consider our surroundings. So over here we have our beaker that we might have in a laboratory, and let's say that we're going to heat it over a Bunsen burner. So we've got our heat going up here into our beaker. So as far as a chemist is concerned, the system is always going to be the part of the universe that you're interested in. So generally for us, that's going to be whatever's inside this beaker. Okay, so we're going to say that the beaker, or the stuff in the beaker, is our system. Okay, so system in the beaker, and that means that everything else outside of that system are the surroundings. Okay, so we want to be very clear what we are considering our system, and then that dictates what becomes our surroundings. And then the system and the surroundings together make up our entire universe. Okay, so if we have a situation where the temperature of our surroundings is greater than the temperature of our system, okay, then we have a situation where we say the heat, or Q, is greater than 0. Okay, so that situation, heat is going into our system. Okay, so here the surroundings, when we have our Bunsen burner is part of our surroundings. Okay, so this temperature is greater than the temperature of our system. So heat is going into our system, which means from the perspective of our system, heat is greater than 0, or Q is greater than 0. So we can make a little arrow there that kind of shows us Q going into our system, okay, or Q is greater than 0. Okay, now if we have the opposite situation where our surroundings are a lower temperature than our system, then that means that heat is going to leave our system and go into the surroundings. Remember, we're always following the direction of the heat flow, okay? We don't talk about cold going into our system or cold leaving our system. It's always the heat. We're always following the direction of the heat. So in this situation, since our system is hotter than the surroundings, we're going to have heat leaving the system and going into the surroundings. So in that case, the sign of our heat, or our Q, is going to be opposite. So there we would have Q less than 0. Okay, so Q going in, that is Q greater than 0. And if we have heat going out, then that would be Q less than 0 situation. Again, from the perspective of the system. Okay, if we were speaking from the perspective of the surroundings, if instead we said that the air molecules out here were our system, then our signs would be opposite of what we just said. Okay, so just remember that everything is from the perspective of what you have designated the system to be in your situation. We could also change the energy of our system through a difference in pressure. Okay, and that's usually accomplished through either an expansion or a compression of the system. So the classical representation of expansion or compression of a system is usually our gas sample, where we have a container of gas with a movable piston. So this is what we would call a frictionless piston, where this bar is able to freely move up or down depending on the balance of pressure between the surroundings and the system. Okay, so once again, it's important to define what's your system, what's your surroundings, okay, because that's going to define the sign of the work that's associated with these changes in pressure or changes in volume, as we'll see. Okay, so here we're defining our system to be the inside of our container, and then the surroundings are everything outside of the container. Okay, so we might have a situation like we had with temperature, where perhaps our pressure of the surroundings is greater than the pressure of the system. Okay, and in that case, the sign of the work associated with that difference in pressure would be greater than 0 from the perspective of the system. So what we would say there is work is done on the system, or work is going into the system. So work done on the system. And we can envision that as our pressure of our surroundings being large enough that this is going to push down on that piston and push that piston down. So work is being done on that system in the container. The other option is maybe our pressure inside the system is greater than our surroundings. So in that case, our P surroundings would be less than the P of our system. And in that case, the sign on work for that situation would be less than 0. Again, always thinking from the perspective of the system. So there we would say work was done by the system. All right, so really the most challenging part of dealing with our changes in heat or changes in work that go into changing the energy of our system is keeping track of their relative signs. Okay, so just remember, always thinking from the perspective of the system. All right, so now we've explored 2 ways that we can change the energy of our system. We can either have heat going in or out of the system, or work being done on or by the system. Okay, so if we want to account for all of those options, we can do that with a nice equation. So our differential equation for our energy. So we would write that as changes. So very small changes, tiny changes, or infinitesimal changes, however you want to say it, in your internal energy. So we designate those small changes by that little d notation. We can say that that is represented by small changes in Q plus small changes in work. Okay, so when we add up all of the changes in heat and all of the changes in work from the perspective of our system, we get the overall change in the internal energy of the system. And this is known as our first law of thermodynamics. Now, if the changes in your system are large enough, so if you get large changes in heat or large changes in work, then we can modify our equation and say delta U is equal to Q plus W. Okay, so same thing, just kind of on a different scale. So the differential form here is for small or infinitesimal changes in our system related to heat and work, and then we can also write it for larger changes in kind of our macroscopic way that you may be used to using in Gen Chem. You might remember that equation from your general chemistry thermo experiences. So when all is said and done, what we're looking at with this first law of thermodynamics is looking for changes in either the temperature of our system, where we look for differences between the system and surrounding, or differences in the pressure between our system and surroundings. Okay, so those are the quantities that you'll be focusing on when trying to get a sense of how much energy is going into and out of our system. So I hope that was helpful in summarizing the quantities that we'll be looking at for looking at changes in internal energy for a system, and I'll just leave you with that hallmark of everything is from the perspective of your system. So this is the key. Okay, so always make sure that you're talking about what's happening from the point of view of your system, and your signs should always work out correctly. All right, good luck with that, and I hope that was helpful.